Andre Ampere experimentally studied forces between current-carrying wires and between a current-carrying wire and a magnetic field. From his experimental observations, Ampere developed quantitative descriptions of the forces. If you have a wire and you take a straight line segment, and I'm going to use small line segments, so I'm going to represent them with differentials, then the force on the segment IDL, which I'll call DF, is given by IDL cross B. So the direction of DL is the direction of the current, and B is our magnetic flux density field. The force is perpendicular to both the direction of the current and the direction of the magnetic field. This equation is just a description of experimental observations. I am going to look at the force on a current-carrying wire in a magnetic field, and I'm going to look at the force on this wire. My magnetic field will only be in the center region, so I wanted to keep this wire as short as possible to minimize its weight. To make electrical connections, to each end I'm going to solder a thin wire, and to the other end of each thin wire I am going to solder one of these thicker wires again. The purpose of the thicker wire is so I can make an electrical connection with an alligator clip. These wires are magnet wire. They are used to wind motors, generators, and transformers. They have an enamel insulation, so that insulation has to be removed from the ends of the wire. I have removed that insulation from this piece, and you can see how the color changes from where I have enamel to where it's been removed. I used a knife to scrape off the enamel, but you could also use sandpaper to scrape off the enamel. Here is the end result. I've soldered the thin wire to each side, and at the other end of the thin wire I've soldered to my thicker wire. I have two magnets with the north pole of one facing the south pole of the other one. And so the magnetic field will emanate from the north pole and enter the south pole. There's a gap between these two magnets, and I can vary that gap. And the smaller I make that gap, the stronger my magnetic field will be. So if I get them close enough, I will have a magnetic flux density field of about 1 Tesla. I have the straight wire in the gap between the two magnets. I have a 9-volt battery with the negative terminal connected to the top here of the wire, and the positive terminal will be connected via this switch to the bottom part of this wire. When I throw this switch, a current will be flowing from the bottom to the top of the screen through the wire. The magnetic field is emanating from the north pole on the right and entering the south pole on the left, so IDL cross B will give an upward force. If the wire pops up, I will have verified that the direction of the force is the cross product between the direction of the current and the direction of the magnetic flux density field. I will now close the switch. And if I keep the current flowing, if I try to place the wire between the magnets, you see it keeps popping out. Let me now close the switch and turn the current off. I will now close the switch, and you'll see the resulting force on the wire pop it up out from between the two magnets.